All right, hi everyone and welcome to this webinar. We will be starting live in a few minutes. So I'm just waiting for everybody to join. So maybe while we wait, you can start sharing in the chat your experience. How are you currently using 3D printing and what are you expecting today with this session? You can just feel free to interact in the chat. Hello, so we have some people from South Detroit. Some Vancouver, great. So far, no mold in Atlanta. Great, there are a lot of people from everywhere. Great, it's great to see that a lot of people are sharing some comment in the chat. Thanks for your participation. So maybe we're going to start just a few seconds more. All right, so I think we can start now. I'm just going to pull my slides. All right, so welcome everyone. Today we're going to discuss how to quickly fabricate short-run injection molds. So this will be a live panel discussion between my two guests, Mark Bartlett from Novus Applications and Jacob Fallon from Braskem. And myself, I will be moderating to this session. So I will let you both introduce each other. Jake, maybe you want to start?
So hello, everybody. My name is Jake Fallon. I'm a technology development engineer at Braskem. I'm part of the 3D printing team. I've been on the team for about a year and a half, but have about 7 years of experience in 3D printing and excited to share what we've done with Formlabs today with you.
And I am Mark Bartlett, the president and owner of Novus Applications, a product development firm based in Erie, Pennsylvania.
Great, and so on my side, I'm Juliette Combe. I am application engineer at Formlabs and conducting research on 3D printing workflow for manufacturing. So just a little bit of housekeeping first. We're going to have a live Q&A session at the end. So if you have any question, please ask them in the Q&A button that you can see here, not in the chat, in the Q&A. And also you can vote on each other question. So we will see the most popular one on top. So today you will learn how to do low volume rapid injection molding with 3D printed mold. And if you are already using injection molding, you are probably producing your mold out of metal by machining or outsourcing them. And hopefully today, after today, you will be able to fabricate on-demand short-run mold to reduce your tooling cost and lead time for small batches. So here's the agenda. I'm first going to give a quick introduction of the process. Then Jake will introduce Braskem, Mark will introduce Novus Application, and then we will have a live discussion to address important topics such as design, post-processing of the mold, injection condition, molding condition, and demolding. And we will end up the session with a Q&A. All right, so first, for those who are not familiar with Formlabs, our vision is to expand access to digital fabrication so anyone can make anything. And we are doing this by creating reliable, accessible 3D printing system for professionals. So we manufacture 3D printer, the resins that go with it, and the post-processing system. And for those of you who are not familiar with injection molding, I want to give a brief introduction about it. So here's a diagram of the process using 3D printing mold. So it first starts with designing the part and designing the mold in a CAD software, then printing the mold and possibly post-processing it. And then you implement the 3D printing mold in your injection molding process system. It starts with mold clamping first, and then some plastic pellets are introduced in the system, and then under high heat and high pressure, they are forced into a mold to give the shape of the part. So this is the injection phase. Then there is a cooling phase to cool down the part and a demolding phase. So here's a quick intro about the process. Now I will leave the floor to Jake to introduce the Braskem company.
Thank you, Juliet. I'm really excited to be here today and be able to share with you all these really exciting challenges that we face and how we've overcome them. So before I get into the details of how we've used the Form 3 with injection molding, I figured it'd be a good opportunity to share with you all just a little bit about Braskem in case those of you who may not have heard of Braskem before can be familiar with what we do from a traditional standpoint. So Braskem at its core, in a very high level, is a chemicals and plastics supplier to the market for products that go into many different parts of our daily life, from food packaging, containers, healthcare products, PPE, the transportation industry, things like bumpers, panels, many different aspects of our life. We touch Braskem products on a daily basis. Braskem is Juliet, sorry, could you go to the next slide?
Sure.
Thank you. So Braskem is a global company with an industrial footprint. We mainly supply polypropylene in the United States, polyethylene in Mexico, a variety of products in Brazil, and polypropylene in Germany. So from a traditional business, things like injection molding, extrusion, we have products that we supply across the world into various applications. But on the next slide, Juliet, thank you. On the next slide, cover kind of the transition. So how is Braskem playing in 3D printing today? So it was about 3 to 4 years ago, Braskem made the investment in the additive manufacturing business. And in the investment, I like to think of in two different aspects. There's from a very traditional sense as a material supplier, Braskem's investing in producing materials to supply to the 3D printing market. And then also from maybe a not so obvious standpoint, Braskem notices the power and the advancements that 3D printing technologies bring to running a business, improving safety, and efficiency, and productivity. So we also utilize these technologies internally. So on the next slide, Juliet, thank you. So on the first area, Braskem produces products specifically for the 3D printing market now. I think a few years ago, if you were to look at the traditional markets for injection molding or extrusion and compared them to 3D printing, you would have seen a big gap between the materials used in injection molding. You'll see polypropylenes used very often, But when you consider it as a feedstock for 3D printing technologies, there's very few products that are available on the market. So Braskem spent the last 3 years developing those products to supply the market. They come in filament forms, they come in powder forms, they come in pellet forms, all to supply those unique technologies. But jumping to that second area, which I think is more relevant to the discussion today, Braskem utilizes 3D printing internally in many different ways. And one of the really interesting cases that I want to share with you all today stems from the situation we were all facing in early March, where the COVID pandemic began to take full force. Lockdowns were occurring, and businesses were being forced to operate in new ways. And Braskem was not immune to this either. So in fact, Braskem was deemed an essential business, and really one of the core products that we supply to the market, which is used to produce the N95 masks, was incredibly important to continue that production at the time. So you may have seen on the news, we had more than 40 employees who actually lived in their plant for 28 days to ensure that that material could go to the front lines and protect those healthcare workers. So we were familiar with operating in these very challenging environments. But as you go through continuing operating in this way, wearing masks, you can actually start to develop, in some severe instances, some wounds, very strong discomfort behind the ears from wearing a mask that frequently. So our vice president came to us, said, hey, our team members are struggling with this. We have employees who need to find some way to relieve the stress behind their ears. So he said, you have 48 hours to come up with a solution if you can do this. He gave that challenge to our 3D printing team. And sure enough, within 48 hours, we were able to, utilizing the Form 3 printer, come up with a solution where we could produce over 8,000 mask straps, send them out to all of our sites to help protect our employees and enable them to work in a more comfortable environment. So on the next slide, Juliet, this is a brief outline of how we solved that problem. Within 24 hours, we were able to have a digital design of a mold. We had that mold printed within 48 hours, and we were making parts within that first 48 hours. And like I said, 2 weeks of production time, we were able to produce over 8,000 mask straps to help protect our team members amidst the difficult working environments.
Great, thanks, Jake. This is very interesting. So that's a great intro on Braskem. Now I leave the floor to Mark to talk about Novus Applications.
Thanks, Juliet. So it's good to be here with everybody this afternoon. For a basic introduction, next slide. At Novus Applications, we're focused on providing product development services. So reading in the chat window, I see there's a lot of product developers here today, and I hope that I really touch a note of where you're at in your professional life. Specifically, being a product developer, that's a pretty generic definition. So specifically, Novus is focused at the consumer packaging sector with an emphasis on injection molded plastics. We like to bridge the gap that we frequently see between the industrial design sector and large-scale manufacturing. So there's a zone in there where the freelance industrial designers have created beautiful images, but we've got to get them fleshed out. We've got to get them ready for market. They need to be able to be injection molded in high volumes and assembled at high rates. We bridge that gap specifically through our experience as tool makers, engineers, and product designers. We have a diverse staff with a lot of depth of experience. From a personal background, I was a tool maker in the trade for 12 years prior to ever getting into injection mold design. I have a background in engineering from Penn State, and then I spent 10 years designing high cavitation injection tools for the consumer sector. So we did everything from bottle caps to personal care, healthcare, things like that. Next slide, please. So we leverage our knowledge base in order to provide our development services from a very non-traditional perspective. We were not your normal product designers first. In short, we were the people historically that built the molds, that did the troubleshooting, that produced the parts, and now we're the individuals that design the products in order to have other people's needs met during that manufacturing process. So before we leave the slide that you see in front of you, these are samples of programs that have personally been involved with the development from the ground up, not only in the architecture of the products, but also in the high cavitation tools. Naturally, some very high volume products that we're looking at. A good way to think of Novus Applications, if you were to walk through the personal care aisle, you would see our work in numerous places. Next slide. So frequently, our customers come to us in the early stages of concepting. It's not uncommon that we're provided a hand sketch, pictures taken with a smartphone from a whiteboard, basic low-level ideation of we need to get from point A to point B. We frequently do complex form creation, volume studies, e-commerce solutions. The upper left image that you're looking at a medical device done for MDM Wound Ventures in San Antonio. And literally this was sent via a fax off a copier machine. 3 guys were talking in the field of what they needed in order to do wound care. Likewise, form studies on the right. This was done for a fabric softener initiative where we were doing volumetric versus bottle shape. Next slide. The largest portion of our work as a company specifically involves integration with larger scope programs. Typically, that means a large team of engineers. So rarely are programs of a large magnitude done individually. Novus routinely interfaces with large and small packaging groups, and we fill a role that utilizes our skill set as manufacturers and tool makers first. That gives us the ability to produce plastic parts for these assemblies. So this slide displays some work of that nature on a product that involved a team of engineers for about 18 months. In that role, I took charge of the architecture, the molding strategies, the injection mold designs, pieces like that. So I feel that programs like this display our very best offerings as a company. So being a small company that does product development, that inherently means we don't have the resources of a very large corporation. So oddly enough, that's been a strange asset to us, mostly because due to the fact we're a small company, we have the latitude to act and react very quickly. We're a nimble group and we get things done promptly. So this lets us be the side of the engineering team that makes the tangible parts, puts them together and does the testing in a rapid response way. Next slide. So wrapping up an overview of Novus, we're still holding true to our roots as manufacturers. We regularly design injection molds, so we do 30 to 40 production molds a year. We design and build numerous prototypes in various forms, anything from steel, collapsing core, down to what you're looking at here is an aluminum tool that we finished up recently. And then the next slide we're going to go into is some of the printed mold sets, and that was a case study done specifically for Formlabs. We're a beta test site for some of the materials that they've tested, and we were brought in on this question of what are you using this resin for, how is it working, and what would you be interested in testing for injection molding?
So thank you very much to both of you for this great introduction. Now we will have a discussion format where Jake and Mark will share their experience. So we have a lot to cover in this panel, so we want to save some time for the Q&A at the end. So we will try to be brief in the answer. But for everybody who's listening, if you want if you have some topic that you want to dive deeper, feel free to mention it in the Q&A and we will come back to it during the Q&A session. All right, so the first question I will have for you two is why are you using 3D printing injection mold today? So maybe Jake, you want to start with this one?
Yeah, that's a great question, and it was a question. It was the first question we asked ourselves whenever we were given the challenge from the VP with a 48-hour time window. So we needed to know what are our options and which option seems the most feasible. So just looking quickly at some of the most accessible options we had, three cases. There's what I call directly 3D printing, which you may have seen a lot of filament machines doing amidst the pandemic, directly 3D printing mask straps. If you look at the two graphs here, it's a fairly cost-effective method of producing them, but it takes a lot of time. You're talking about sometimes 15 minutes per mask strap, which is not feasible when you're talking about producing 8,000 mask straps. I think I might still be making them today. The second option was a metal injection mold. Certainly the traditional way to solve these problems, but amidst the pandemic, those toolings are very difficult to do logistically, and they're still rather expensive. So although we could get a pretty fast production time, you're looking at a fairly expensive tooling cost, and then the lead time, if you consider that in the time to produce a mask strap for that metal mold, is fairly significant. So I think obviously by the graph, the clear winner here was, can we 3D print an injection mold? That's going to make our cost extremely low because the cost of material to produce that mold is very low. And then also the turnaround time to actually produce the mold and do redesigns is extremely efficient. So we're left with a very low cost per part and a very low time. It's the total time per mask strap.
So I believe you ended up around 90% of cost saving and time saving, right?
Yeah, if you turn these into percentages, the case is very clear. What's the best option here?
Yeah, those graphs are very good. So just to make it clear for you, metal injection mold was to outsource, right? To outsource the mold. Yeah.
We didn't have capabilities to do that internally, so outsourcing was our option.
Yeah, exactly. So for you, Mark, I know you are in a different situation because you actually have a CNC machine in-house, so you wouldn't need to outsource. So maybe you can tell us a bit more about what were the advantages for you.
Yeah, absolutely. So it's kind of funny because one of the things to observe is we do 3D printed molds to explore the possibilities. So part of it is it's there, we want to do it, we want to try it. And if we don't explore this, then we're falling behind where competition means that we can be. Additionally, there is a speed of iteration, lower overall investment cost. So I don't require a lot of the high-end machines in order to do simple, small, low-end runs. We'll get more into that later.
Okay, perfect. So now that we know why you were doing that, maybe let's go into how you were doing this process. So designing the part and the mold is critical. It has a large influence on the process. So I would like to ask you, what are your recommendations and guidelines for design? So first, to design the part, I would like to start with a Braskem part because it's a very simple design of a mask strap. So maybe Jake, you can tell us more about it.
Yeah, I think we had a great design to start with. This was a fairly simple geometry, so we weren't having to push the limits with intricacies or engineering tolerances at first, which I think certainly helped us produce a lot of parts very quickly. But we definitely had a couple key learnings that enabled us to push the limits on production rates even further. And I think a lot of them it will come back to reducing pressure, reducing shear, simplifying flow patterns to reduce those pressures and shears. So this can help you can solve these issues by rounding corners where possible, reducing how many flow paths you have. So if you can keep your flow paths linear in the mold, based on your gate location, that can definitely be helpful too. And then be cautious whenever you're using very thin features like thin ribs that require traditionally high pressures to fill. Those can be difficult to fill out sometimes. So if you can tailor your design to fit those guidelines, I think you'll be in a much better chance for success.
Yeah. And you, Mark, you were designing a threaded cap, right?
Yeah, and I wanted to do this mostly because it starts to represent some of the things my customers would typically be after. So it's not uncommon in the cap and closure industry, you're going to need to generate threads. But stepping back for a second, one of the things you'll see in Jake's also, flat parting lines are highly desirable. Anytime that you can split on a flat plane, that's a big win for your part design and then your mold design. I noticed that was one of the questions in the Q&A section coming through. So we emphasize trying to keep parting lines flat. That's not realistic in all parts. So we have done it on contoured parting lines. It just takes a little more attention to detail. Secondarily, maximize draft. We're going to come back to the demolding conditions, and any time that you can get excellent draft conditions, you want to get upwards of 2, 3, 4 degrees if you can. Then lastly, we always try and get an early plan for demolding. The sooner that you can figure out how you're going to get your part out of the mold intact and keep your mold intact, you'll get many more cycles out of your printed mold.
Okay, great. So now we have some good recommendation on the part design. Once you have the part design, you design the mold around it. So specifically knowing that it will be a plastic 3D printed mold and not a metal mold, metallic one, what would be your design recommendation?
Yeah, there's a different approach to making a good 3D printed mold, and those approaches will be different from a metal mold. So it's definitely good to step back and think about what's actually needed for the part to be molded. And very clearly, I think there are differences here. So specifically right off the gate, no pun intended, that a large gate is much more advantageous here whenever you're working with a 3D printed mold. Again, you're reducing pressure where you have a larger flow path. You're reducing shear by increasing the volume for flow. Any opportunities you have to round off surfaces, as you can see in my CAD drawing here, it's going to help reduce shear and wear over time. We've incorporated what I'll call a large vent at the end of most of our flow paths, at the end of our cavities. This is definitely different than what we see in metal molds. Metal molds, you'll see an air vent. These are very thin sections to allow air to escape while you're molding so you don't get burning in the mold. In our case, these are essentially much thicker vents, large enough to allow plastic to flow out. So what that allows us to do is two things. We can reduce pressures, but if we have uneven flow, non-geometrically balanced flow within our cavity, and say one side's filling out more than the other, instead of ramping up pressure to help get better fill on the other side of the cavity, we can simply just overflow the one side of the cavity to enable the other side to continue filling. And then as Mark said in the previous slide, draft. The more draft you can add, the better. If your surface allows it, if your engineering tolerances allow it, add draft. It's gonna help with mold release. Typically, I think in metal molds, you're talking very low percentages, maybe 1%. In our case, we're talking up to 4 or 5% if you can allow for it. And then on the other side of the cavity, these are things that you normally don't really think about with metal molds, but you have the opportunity to control them here in a 3D printed mold. Backing out of large molds can help. These are made from these are made from curing materials, these molds. So whenever you get very thick cross sections of the mold, you can actually have a difficult time curing a very thick inner part of that mold. So we used a technique that helped a lot, what I call backing out. We're only putting material where we need to resist those cavity pressures. This allows us to get better curing on the back, and we're also saving material usage that isn't making a big difference in the longevity of the mold. And then also, as Mark mentioned, alignment of the parting line. If you can keep that parting line very simple, you're going to have a much better performance. So in our case, we were actually able to keep a single cavity and press up against a metal flat plated side of the mold. So it allowed for a great kind of close off around the cavity, and I think it prolonged the longevity of our mold.
Okay, so it's good to see that you both have a similar recommendation, and that you made this pretty similar observation. So Mark, also for your design, I think you also had some comment on the gates and vent.
Yeah, absolutely. I think that we'll all notice that Jake and I started at very different places and ended up in very similar conclusions. Gate for your fill, you want to keep them as large as possible. Likewise, to minimize your pressures, we always try to allow vent and overflow, especially in an area that we can trim readily. So we openly admit that one of the main goals is keeping pressures low so that we don't end up destroying our stag. Next slide. So a couple other pieces of advice. As we were looking at the cap, if you have the possibility, if you're molding a hole through your part, don't just do a simple butt shut off, but project the core through and do an interlock. So a conical interlock will help keep that core in place and keep deflection at a minimum. Even though our mold was done in rigid 10K, it's capable of handling it. So this freestanding core did quite well, but proportionally it's not very tall. So if the diameter is small and the length starts getting long, try and interlock anything you can, otherwise you're going to break those cores off. Likewise, one of the things that we do is we allow for grooming of critical dimensions. Now, if you notice Jake's mold, his was done in an entire printed cavity. The gate came in on center. The melt never had to cross a transition. Ours is put inside of a nest inside of a metallic mold set. So anywhere that our flow is crossing over that seam line, you have the potential for flash. Therefore, our part outsides are groomed to fit the pocket, so we're not flashing down in between. Likewise, where the core fits inside of the B-side cavity block, we left material there and trued the outside of the core up, and we ran a reamer down through the hole. So we're fitting our core diameters, and then we're fitting our butt shutoffs and our stack heights so that we are maintaining the best quality of molded part as we can. Next slide. So additional considerations. This core is of great interest. Avoid sharp corners and thin molding conditions. One of the questions in the Q&A was regarding thermal transfer, and naturally a printed mold set doesn't draw the heat out at the same speed that metallics will. So when we printed the cores for this mold, we printed 6 cores, and we would alternate between the cores as we were molding to keep the cores as cool as possible. That helps to a great degree, but towards the end of the sample, we were increasing pressures to see what the stack would handle. Eventually, the thin corners up on the top, when we would demold this core, they were breaking off. It just couldn't handle a demolding circumstance like that. Finally, the last point being, ensure that your demolding is robust. You want rapid access. You want to make sure you have adequate force to get it out of there. Someone asked the question about ejector pins. We don't shy away from ejector pins. We have no problem with that. So we always look at the mold and say, how are we going to rely that we're getting all of the plastic out in a consistent way without distorting the part or destroying our printed parts?
Great. So those are great recommendations to really keep in mind when you're designing or thinking about the demolding and thinking about the whole process. How is the process going to happen actually from start, from the design? Thank you for all those recommendations. So next question is, once you have the design, how do you approach the printing and the post-processing?
Yep. One of the things that we were considering as we were approaching this, I want to call attention to 2 main groups on the screen here. The large square blocks would be our cavities, and in plan view, we're looking at the cylindrical thread cores tipped on an angle. So let's talk about those thread cores first. When we were working through the rigid 10K setups, we were talking with Formlabs techs about the best possible way to get a truly round core in a robust setup. When they looked at this print orientation, they quickly recommended don't print the cores tilted on this angle, but rather adhere the cores directly to the print bed and do them in an upright cylindrical fashion. Then we closely inspected them at the end of printing to see what we would get. The roundness condition was extremely better. That was an excellent piece of advice from them. Now, if we consider the rectangular blocks on the screen, one of the things that we know we have to do is to groom our blocks to size and to be square. So we tip our blocks up on a 20 to 30 degree angle in one axis only. specifically so that when we start to finish the block, we've done it via sanding, a simple milling machine operation, things like that. But you need to have a couple square sides that you know you're working off a good reference edge. Otherwise, your blocks can be out of parallel, out of size. So we closely watch orientation, then we trim and clean, we do a full cure, and then we do some minimal grooming. Emphasis would be we did not touch the molding surface at all. So all of the molding sizes, the logos, everything was done. Thank you, Juliet. Here's a sample of our inspection point. So when our block's printed, you can see there on the screen, the +2, the +4, that's written in thousandths of an inch. So we were material heavy in the Y direction, +2 thousandths. And when miking over the length of the block, we were +4 thousandths. So there is a little bit of variation. Again, that was done early in the 10K resins test phase. So during beta, those were numbers that Formlabs was working on improving accuracy of print. But that's something that we watch closely because we know if we flash the mold, it's going to be problematic. We won't be able to demold quickly, and then we risk breaking the part trying to get the plastic part out of it.
Yeah, thanks for this recommendation. For you, it was quite important to finish the mold. For you, Jake, I believe you did some light finishing as well.
Yeah, so for us, we had a different engineering approach, I guess, to or engineering requirements for our molds. So in Mark's case, he's got very tight tolerances that he's trying to fulfill. For our case, we're really just trying to generate a shape to fit the need. So post-processing for us, I guess there's a couple challenges. One, if we didn't need to mar the cavity surface with support materials, we wanted to avoid that. And so our recommendation is if you're gonna, if you have to orient your part and it has to have support material, orient it so that your supports are on the backside of the mold and you're not going to have any artifacts on the cavity surface. For our mold, since we were producing such a large geometry, actually we had to tilt it to be able to fit into the Form 3 printer. So we're really at the limit here of the size of parts we can make. We were getting very thick cross sections, which required a lot of curing, and that curing can happen unevenly in some instances. So you can get warpage. In our case, the warpage was extremely minimal to get the tolerances to fit into our metal mud mold, if you will. We just required a slight bit of sanding to be able to make that fit a little more snug.
Good. And so once you are done with preparing this mold now, let's see what are the injection conditions. So what would you recommend for molding condition? So I put some data here on each of your molding conditions so that the audience can have it as a reference. Maybe you can give us your main recommendation and consideration for this process.
Yeah, I've seen a lot of questions coming up in here about pressures and temperatures. So hopefully this is helpful. But I think it's critically important. This is a big part of the unknown when using a 3D printed mold. But it's extremely important. You can go through all those design recommendations and make a mold. And if you don't have the appropriate processing conditions, it's never going to work. So you really need to take care with processing. And the key trends that we've outlined previously and restated here with some actual numbers is low pressures. In our case, we're using about 5,000 PSI injection pressure. This is definitely going to be dependent on the part we're trying to make, but starting low and going as high as you need is the trend you should go. Injecting slow, reducing shear. You don't want to pack material very fast into these cavities and develop high shears. We inject very slow. We're not processing as quickly, but we still get the part in a reasonable time. Clamping pressure is critical. Keep as low as you can. Since we're not packing out with super high pressures in these molds, you don't need as much tonnage to keep the plastic in and prevent it from flashing. This will be dependent on how close of a parting line you can keep, but keep the pressure as low as you can. In the end, we were able to achieve 30-second cycle time which is, I think, very efficient and comparable to what a metal mold would be. We were running in semi-automatic, which means we didn't have ejector pins. We had a operator pulling each shot out. This was just because we didn't have time within the 48 hours to dimension out all of those ejector pins. And we knew we'd be watching the mold operate on a more continuous basis. With these strategies in this geometry, we were able to achieve 1,500 shots per mold, and we could have kept pushing those molds even further. That was with the high temperature resin. I'm very optimistic that if we were to use the new rigid 10K resin, we could push those numbers even further. So in the
next step.
Yeah, that's the next step. So in the end, those 1,500 shots for one mold produced 3,000 parts. The shot is in my hand, you can see there. So that's 3,000 parts, which is a huge step. It depends though on how complex your part is.
Mm-hmm.
So Jake, before we leave your slide, could I ask a question there?
Yes.
What melt resin were you using?
So this was a polypropylene resin we were using. To get the best results, in lowest pressures, you want to use something that has a rather low viscosity. You don't want to have a lot of resistance to flow because that's just going to mean more pressure. So if you can use a higher melt flow resin, I think you'll have a little better success with the fill out of the mold. I believe in this case, we were around a 30 or 40 melt flow. But again, those melt flows are going to be correlated to the specific resin. So if you're using ABS or polycarbonate or something else, you'll need to just try and go on the higher end of the melt flow range.
Great. So so that's a good transition to the next. So to Mark's mold, that is a more complicated geometry. So Mark, maybe you can share what were your conditions?
Absolutely. So Jake, I was asking because ours correlates to that as well. Our polypropylene, I believe, was like a 30 melt that we were running. We try and run on the low end of temperature. So I believe Jake made his mold out of the high temp resin. We're running in the 10K rigid. So we're trying to keep down in the lower injection ranges on this. Our pressure, we were running about 9,500 PSI on this. I mentioned earlier that as we got to the end of the run, we wanted to see what we would get cycle time wise and quantity wise. We knew that those would be points for the discussion today. But when we got towards the end, we started taking that pressure up. Our cavity stacks failed at about 11,000 was where we saw failure happening. The 50-second cycle time should be noted for a couple reasons. Number one, we have a pretty thick wall. So one of the questions in the Q&A was asking regarding why are your cycle times lower? Well, part of it is you can't get the heat out, but some of it is the nature of it's a very manual and labor intensive process to pull the stack, manually disassemble it and reassemble. So Jake was running in semi-automatic. We do molds like that, but when we're running something of this nature, we were manually taking that core out. So it's not a very fast cycle time. I think we could be molding, maybe 35 to 40 seconds if you were able to really speed that demolding process up. And then, as said before, we saw hundreds of shots. We were extremely pleased because a lot of our customers are just trying to get a product developed and get 40, 50 samples in hand so you can assemble, test with real molded parts.
Yeah, this is definitely very impressive for this type of geometry with a 3-part mold and very thin feature as well. So one last question on the process. What are your strategy for ejecting and demolding actually? Maybe Jake.
Yeah, I think Mark's got, a more comprehensive approach to the ejection and demolding. For us, like I mentioned, we were really trying to produce parts as quickly as possible. So, if you're in a pandemic, maybe you'll use our approach, but maybe in a more ideal world, you'll be able to incorporate ejector pins and have a little more optimization there. So for us, the key was, we needed to make sure that the parts could come out cleanly. That was definitely helped by the draft angle that we mentioned earlier. And Mark mentioned too is really important. And then also we were using a mold release spray. Maybe a spray every 15 to 30 minutes just to recoat the mold. And I saw a couple people asking for For our mold spray, we were using a silicone-based mold spray. I believe the brand was actually called Mold Spray. So hopefully that helps. It seemed to work very well for us.
Great, thanks.
So interestingly enough, oh, go ahead, Juliet.
Oh yeah, I was just about to ask you to tell us about, well, you already start telling us about the demolding, but if you have some stuff to add.
So as Jake was talking about mold spray, we were rather surprised because, of course, we started the mold with mold spray, and part of the process, we want to see how it's going to behave without. We were running this the last 60 to 70 cycles without putting mold spray on at all. You would notice it when you're taking the thread core out, but the ejection itself was not a problem. One of the things we were doing to eject this part, if you look at the image on the left of the B side of the mold, we were ejecting the center thread core with a large diameter ejector pin behind that core. So when it ejected, we had the whole thread working for us, and we would demold the brim automatically, and then we would demold the thread manually. So yeah, mold spray, that's your friend. You want it. We use Slide brand. Not that that's, yeah, it definitely helps, but not that any of the mold sprays you typically use, I'm sure would work just fine.
Mm-hmm. Okay, so that's definitely a very good tip. So one last question I have to conclude this will be, what is next for you? What would you like to explore next? So Jack, do you want to start?
Yeah, that's a great, we already touched on, you know, the next materials, you know, the 10K resin is certainly on our radar. It's something that I think is going to perform very well in our scenario. You know, just a note, the high temperature resin which was what we used, was the highest strength material that I was able to find at the time, which is why we picked it. It's not to say that other lower temperature mold materials that Formlabs provides wouldn't work. I think the 10K resin actually works quite well, and for materials that don't process at such high temperatures could be very nice. The other aspect that we're really excited about is the Form 3L. You know, we were pushing the limits on what size mold we could make, and you know, it's trying to squeeze it into the build plate as best as we could. So the opportunities that the Form 3L, which is a larger version of the Formlabs Form 3 machine, the opportunities that enables is really exciting. You know, can think about building more complex interconnected molds that make larger cavity parts. So I'm really excited about that as well.
Yeah, you told me that you already had a lot of projects in mind for the
yeah,
Form 3.
I have more projects, yeah.
It's great.
Certainly.
You just need it now.
Yeah, exactly.
Great. And what about you, Mark? What would you like to try next for this process?
So what's on our horizon, I think, is we're looking at hybrid methodologies. Jake and I even talked the other day regarding how do I put in a metallic gate insert. So specifically, there's some advantages to be gained from utilizing metals. Emphasis on the moment that you round that corner, you start requiring some accuracies within that printed part. So it does require a little more grooming, but some of the biggest things to be gained is you can create complex form in a very, very expedient way, and then couple them together with the metallic needs where you can exploit that advantage. So that's what we're eyeing up next.
Great. Well, thanks a lot. So that will be the concluding words. So thanks a lot to both of you for those great recommendations. For everyone who's watching us, if you like to know more about Jake's and Mark's case, we have a white paper that is giving some more info, some data about it. It's also feature another case of a customer using a manual press. So it's a good solution if you are not familiar with injection molding and just want to start the process. So it's a company called Holymaker, so you can have a look at it. And if you would like to try rigid 10K resin, our new resin that we launched really not long ago, you can contact us or your local reseller, and we can send you a free sample.